This is Professor Hill. Today we are going to start to talk about ocean chemistry. The title may make it sound kind of boring, but it really isn't. The chemistry of the ocean is the basis of life on this planet. Life evolved in the ocean, and for life to have moved out of the ocean, we actually had to carry the ocean with us. That's why we're mostly water. That's why the water, our tears, and our blood is salty. We came from the ocean, and the ocean's properties are what made us the way we are. So take my word for it. This is interesting. All right, so seawater contains dissolved solids, liquids, and gases. So where do the dissolved solids come from? You should know the answer to this one already. This is a little review. Primarily rocks, right? Remember we talked about the weathering of rocks and how water is the primary weathering agent on this planet, and how because of hydrogen bonding, let me see if that's in the next one, water's actually taking apart rocks and minerals molecule by molecule. Well, no, I guess I didn't have the, because of hydrogen bonding, it's taking them apart molecule by molecule, right? Because it has the positive and the negative ends, and so it takes the positive and the negative ends of the elements out of the rocks, adds them to the rain, to the water, which goes into the rivers, which goes into the ocean. We have these ions, and it makes our ocean salty. Where do the gases come from? Well, primarily the atmosphere, right? That's pretty obvious. Gases diffuse into the ocean, and they diffuse out. So you've got a new vocabulary word there, diffusion, right? The random movement of molecules from an area of higher concentration to an area of lower concentration. Now, the concentrations of the gases in the atmosphere and in the oceans aren't exactly equal, but right now they're at equilibrium. That's another word you should know. I should add that in there. Equilibrium is just what it sounds like, where the processes that are going one way, like the input into the ocean, is equal to the processes of the other way. So the gases that are diffusing in are pretty much equal to the gases that are diffusing out. So what about additional liquids? Well, additional liquids are mostly going to be water, and that'll, change the salinity of the ocean, make it more or less salty. And basically it comes from rain, snow, melting ice, precipitation that runs off the land and goes into the ocean. Another vocabulary word you need to know is residence time. So all these ions and elements that are in the ocean have a residence time, which is the average amount of time that that particular element stays in the ocean before it cycles out. Everything on this planet cycles. It's kind of a living system. That's what keeps it fresh and alive. If things stopped cycling, it would all go pretty much downhill to decay. But we keep recycling all the major elements, especially the ones that are needed for life. Yes, the residence time can be very, very short. It can be minutes or hours or days, but it can also be millions of years. The average amount of time that an element stays in the ocean, that's its residence time. We already talked about this, so this is review. Again, let's see what we got here. I did talk about hydrogen bonding, right? Our little water molecules have positive and negative ends, and that's what causes them to weather the rocks. The ocean is 96.5% water and about 3.5% dissolved ions. Positive ions called a cation, and negative ions called an anion. When a cation and an anion are attracted to each other and combine into a compound, we call those compounds salts. Again, this is all pretty much review. That's showing you that picture right here, that most of seawater is what it sounds like, water. And then all the dissolved things that are in it are this little tiny cube here. And if you take that and break that down, you see that most of the dissolved ions in the ocean are really of two types: chlorine, chloride, and sodium. And sodium is positive, chloride is negative. They combine together, they form a salt, the salt that we call halite, the kind that we use for our food. So that's why the ocean tastes salty to us. It has all these other ions in there, and the positives and negatives can combine in different forms, but the main constituent of seawater is, besides the water, is sodium chloride, salt. These are some of the other more common salts or compounds that are formed by the addition of anions and cations. I won't ask you on a test to have memorized this whole list. I might ask you, well, I'll expect you to know halite, right? Sodium chloride. The Na stands for sodium, the Cl for chloride. The top three are fair game for a test. So gypsum, calcium carbonate, and halite, I would expect you to know. Now this is a picture that shows you in color and in contours the salinity of the ocean. As you can see down here at the bottom with the scale, the more red it is, the higher the salinity is, and the more blue it is, the lower the salinity is. And with salinity, we're not talking about just sodium chloride, we're talking about all the salts in the ocean, okay? So you can see that it's not equally distributed. Towards the poles, there's less salt. In the Atlantic Ocean, it's much saltier than the average in the Pacific Ocean, but you can see that there's areas that are more salty than others. Why? Why does this change? There's two main reasons, as I have written down right there. High evaporation, so if you have an area where the water evaporates faster than rain comes down, it concentrates the salts and makes it salty. The best example of that here actually would be the Mediterranean Ocean, because it's kind of trapped in there. It can't interact with the ocean all that well, and it evaporates a lot more than fresh water from the ocean can come in, all right? High runoff. I'm hoping I've got a little video on that, but the reason the poles are less saline is because the ice melts. You know, the ice that forms during their wintertime melts, and it dilutes the water, because you can't have salt in ice. Salt melts ice. Let's see what this is. I hope that this is a little, no, guess not. No luck there. Okay, this is kind of nice. Let me see if I can continue recording. Let's see if I can show you this. So this is some satellite data of a year. I don't know what satellite this is. It's a NASA satellite thing. Let me get this over here. Boop. And it's a year's worth of salinity data. Again, the reds are high, the blues are low. Let me turn it on, and hopefully.
Earth's climate and the circulation of deep ocean currents are strongly influenced by the saltiness of the sea surface. So why don't we have detailed maps that show its rapid changes? Well, now we do. After more than a year of continuous measurements, NASA's Aquarius instrument aboard the Aquarius SAC-D spacecraft has given us this new space-based view of sea surface salinity.
So wait, let me just hang on a minute here.
A closer look at the data,
because he's boring me, and I could probably explain this better. All right, let's just put that in. Okay. So, hold on there. All right, so again, we're seeing our, and you can read it later if you want, or look at this, but they're looking at the North Atlantic. They're saying, look, it's sort of salty there. Are they going to explain why? They're saying it evaporates a lot, and so that causes a lot of salinity. But you can see that there's a lot of blue water coming out down here. That is from the Amazon. That drains the rainforest in South America. Over here, they're saying conditions are different, right? There's a lot of rain there. There's a lot of storm systems. That's where, I'm trying to think of the name of it. Can't think of the name of it right now. but there's a storm system that goes periodically through there, and there's a lot of storms, and so it's diluting the water with rain. And here they're showing you the Amazon. There's also rivers over here in West Africa that drain out, and so that's what's causing the blue over there. And as I told you before, up in the higher and lower reaches of the planet, the melting ice makes the salinity go down. Okay. All right, so now we need a little bit of, let me get this back here, make sure it's still recording, hopefully. Don't see anything. Oh well, we'll hope. Gotta get some vocabulary in here again too. We're talking, the ocean is a solution. It's made of a solvent, which is the water, and the solute, which is all these ions and the salts that are in there. Those are that's the solute. This is a reversible process. You can dry an ocean out and get the solute back out. All right. I don't know if I talked about this earlier with geology. I hope so. But precipitate rocks are what happens when oceans dry up, because over geologic time, the sea level rises and the sea level falls. So we have oceans that have extended as far inland as, well, all the way through the middle of North America. And then when they go away, it evaporates out and it leaves the salts behind. This, just to give you scale, this is a salt mine in Europe. And you can see this little railing down here I pointed to for scale. So all of that is salt. All of that was from an ocean that dried out, and piece by piece, as the ocean dried out, the salt sunk down to the bottom when it couldn't stay in solution anymore and started to pile up. And look at all that salt you've got. It's cool, hey? Do all the dissolved solids come from the dissolution of rock? No. How do we know that? Because the salinity of the rivers that are coming into the ocean are not the same as the salinity of the ocean. So what's changing the salinity of the ocean? What's causing it to be different salt salinity? Well, we got four, and I expect you to know these four. We have volcanoes adding ions and dissolved solids. We have groundwater. We have hydrothermal vents. And we have living organisms. I should have just put living organisms and not decay of, because living organisms cause the change in the saltiness of the ocean in many different ways, not just from their decay. But let's just start with volcanoes. You know, we've always had volcanoes. We always will have volcanoes until the planet dies, pretty much. And when they explode, they let out an awful lot of gas and water vapor. Water vapor is actually one of the main constituents of a volcanic explosion. But they also have, there's dust in there, right? It's mostly sulfur and chlorides. So those two words, those might show up on a test. You know, what do volcanoes add? What about groundwater? Now, in case you don't know what groundwater is, I'm trying to show you with this circle here. Groundwater is the flow of water underground in sediments and rocks. All water flows downhill, right? We know that, right? Waterfalls don't flow uphill. And all water eventually goes to the lowest place it can, which, if it's around long enough, will be in the ocean. All water, the water in our bodies, the water in my tea, the water in the sky, it's all been in the ocean, probably most of its life. And right now, we're just temporarily borrowing it. Anyway, as groundwater moves through the ground and goes to the ocean, it does the same thing underground that it does above ground. It weathers. The hydrogen bonds pick up, you know, positive and negative elements and ions and takes it with them to the ocean. around here, we especially know that because our water is very hard here. That water has dissolved ions in it, mostly calcium, calcium chloride. Yeah, mostly. Oh, here we go. Here's our most common elements that you have in groundwater. I am not going to ask you to list these on a test, but I do want you to know that groundwater carries dissolved ions to the ocean. Number 3, hydrothermal vents. Hydrothermal vents are the product of our mid-ocean spreading ridge, which I explained earlier, how the magma is coming up. The magma is coming up, it's cooling, it's becoming igneous rock, and because the magma keeps coming up in this mid-ocean spreading ridge, it moves the rock aside, right? And it keeps moving aside. Well, when you have rock and you move it, you tend to get cracks in it. Rock doesn't like to be moved. So when you have cracks in the magma, that means what you see these blue arrows here, this is indicating that seawater is getting down in the cracks and getting near the magma. So when you have cold ocean water, and we already know that when it's really deep, it's pretty close to freezing, you know, it's only a few degrees above freezing, and it's hitting that magma that's like 1200 degrees Fahrenheit, depends on the magma, you know, magmas vary in temperature, but it doesn't matter. It dissolves some of the elements from the magma into the water, and it comes out the top in what we call a plume, and it's either going to be, they're also called smokers, a white smoker or a black smoker. Depending on the elements that are in it, it makes it whiter or blacker. There's a picture down here of a black smoker. Now, sometimes they're showing, again, I won't ask you all these on a test, but I do want you to know that these dissolved ions are taken out, and the mid-ocean spreading ridge, as you hopefully remember, is really long, probably about at least 10,000 miles long. So this is going on a lot of places underwater. It's adding, through these smokers, ions and elements into the ocean and changing its salinity. Also, it's taking ions and elements out because it also causes some of these ions and elements to chemically bond to each other and get precipitated. You see this smoker here, how it's on a little, we call them a chimney. Sometimes when those things are coming out, it hits the cold water and it immediately causes it to go back to a rock stage instead of being in the dissolved stage. So it's taking things out and it's putting things in, but mostly it's putting things in, all right? So it's changing the salinity of the ocean. Okay, organisms. Again, should take out the word decay. I got to take that out twice. Organisms add and subtract to the salinity of the ocean. And I have a really neat video here, if I can keep recording. A really neat video here that I'd like to show you. And the volume will probably be way too loud, so I got to make sure it's not going to blast us. And I'll try and play it a little bit. So this is a part of a video called Earth from Space that's in our library here that you can look at. And it's basically telling us how we can take satellite data now from the satellites that are zipping around overhead, and we can learn about how the Earth works in ways that we couldn't before, because as humans we're kind of small and we can't, number one, be everywhere, but we can't. Before, you know, there were places we couldn't go, like down to the mid-ocean spreading ridge and stuff like that. We can learn about these places now through satellite data. So right now they're talking about the bottom of the ocean and how the magma that's under it causes the bottom to rise and fall, and how they can see that.
Now, satellites can actually see the crust of plates moving around. We can see bulges, dips, where the magma is moving around underneath the crust.
This animation shows the swelling of Mount Etna in Italy as magma accumulates beneath it over 9 years. When the volcano erupts, the land sinks back.
So we're getting a picture now of what the world looks like under the crust and how that affects the other dynamic processes of the so-called solid Earth.
Every day, dozens of volcanoes around the world are erupting, while 4,000 earthquakes shake the ground. Our Earth is dynamic, constantly ejecting gases and magma from its depths, and some of this activity has a vital impact on life. The secret to understanding how lies deep beneath the ocean surface. Here, a crucial chemical reaction takes place between molten rock and deep ocean water. The JASON satellite's sea surface mapping radar reveals a chain of active volcanoes a mile and a half down at the bottom of the Pacific Ocean. This is where that critical interaction between molten rock and freezing water takes place. This footage was taken with a remotely operated submarine, also called JASON.
That'd be a white smoker.
Lava and superheated gases spill out of cracks in the ocean floor, known as hydrothermal vents. JASON reveals what happens when cold ocean water penetrates into the cracks. A magma chamber below heats the water to up to 750 degrees Fahrenheit.
That's a
In
black
the pressure
smoker.
environment inside the cracks, the dense, salty water actually dissolves the solid rock. Complex chemical reactions take place, producing minerals containing sulfur and iron. These are nutrients that living organisms need to survive. The seawater, now loaded with minerals from inside the Earth, streams out of the hydrothermal vents. These nutrients feed a thriving ecosystem that includes shrimp and exotic creatures like cucumbers. The deep ocean currents carry the leftover nutrients away. Over thousands of years, they circulate through the oceans, ultimately rising to the surface and contributing to an amazing explosion of life.
All right. It is an amazing explosion of life, but
And we can see this
I'm going to
activity with
say
NASA's
that
Aqua satellite, which is equipped with instruments
later on. You can watch it if you want. You can watch it if you want. You just go to Films on Demand and look for minute 56. But I'll show you that later when we get to primary productivity. Because I know that we all really want to see the animals, right? We all want to see the animals. But we got to understand how the ocean works and why it is the way it is. We don't have to, but isn't it better to understand why we are on this planet the way it is? I was thinking about it just this morning. I was thinking, you know, a lot of people think this planet was built for us. No, we were built for the planet. The planet is what created us the way we are. Okay, biology. Now remember before I said decay, I've got to take away just the decay because there's uptake and removal. There's removal, I'm sorry, let me get this straight. Biology, living organisms, remove things from the water. They uptake some of the minerals because they need some of the minerals, especially for shells. There's these two chemicals I will expect you to know. Calcium carbonate, and this is the chemical formula, I expect you to know that, and silica, SiO2. I expect you to know those two chemical formulas and what they mean, because basically those are the two formulas that the sea animals have decided to make shells out of. So they need that stuff dissolved in the ocean. They need calcium, they need carbon, they need oxygen, and they need silica. They need all those things, and because they're positives and negatives, especially oxygen is negative, they can combine them together. So they're taking stuff out of the water. Now when they die, you know, that stuff eventually goes back And this is a horrible picture. It's the only one I could find. This is supposed to be the ocean, and here's a little boat, and these are all little sea creatures. They're supposed to be microscopic, and how they die, and they can end up on the sea floor and accumulate and make rock, okay, carbonate rock. It's called carbonate rock because there's a lot of carbon in it from the dead animals. Now, and here on the left, that is supposed to be, again, a picture of marine snow, which I believe I've talked about earlier. Most of marine snow is microscopic, and we can't see it. But it's these little microscopic creatures dying and falling to the bottom. A lot of them get eaten before they ever hit the bottom. So again, those minerals that went into their shells and their bodies are being sort of recycled, right? Something bigger is eating them. If they end up on the ocean floor and they get turned into rock, that's also removing silica and calcium carbonate out of the water, as well as the other things that are in animals' bodies. Let me see what this is, if this is anything. Nope, doesn't look like anything. Uh-oh. Get this back here. Better be still recording. Okay. All right, and we talked about the Earth already. We've already talked about subduction, but I want you to see in action, you know, the removal from the salinity of the ocean of calcium carbonate and silica from the shells of dead animals and plants. Oh, that's the wrong one. Whoops, that can't be the right thing. Somehow that got mixed up. Okay, let's go back here. Control C. All right, good. This is a good one. And a good review.
It happens because hot rock rises, heated by the earth.
Okay. Never know. Just never know, do you? All right, let's go back.
It happens because hot rock rises, heated by the Earth's core.
There's a mid-ocean spreading bridge.
Rock spreads in two directions and goes sideways. It begins to lose heat. Eventually, the much cooler rock sinks back down. Through this spreading process, the Earth's crust is very slowly dragged apart. And it's this that ultimately causes the continents to move. Where the plates collide, the rock on the seafloor containing carbon from the dead plankton is carried deep into the Earth. As it descends, this layer of rock is heated, so the rock melts, releasing carbon dioxide. And gas is returned back into the atmosphere during an eruption. The remarkable cycle is complete.
And it is a remarkable cycle. There's so many remarkable cycles going on our planet all the time. And it helps to understand chemistry just a little to understand them. Now, and I have to give decay its place. You know, if an animal dies and it just decays and nothing eats it and it doesn't get buried or turned into rock, right? As anything decays, the constituents break down and are returned back to the environment. So that's a way of changing salinity of the ocean, but that would be a very minor part, right? As far as big biological animals, like, you know, seals and porpoises and fish and stuff. The little biological organisms, the microscopic ones, are the big players in the ocean. They make up most of the life on this whole planet. So they're the ones that we're really talking about when we're talking about biological organisms, the little guys.